There is a planet in our solar system that rolls through space on its side, spinning like a coin thrown across a table, its poles facing the sun for decades at a time, while its equator freezes in permanent shadow. It is the coldest world in the solar system. Its magnetic field is broken, not tilted slightly, as on Earth, but lurching off-center by 59 degrees, offset so dramatically from the planet's core that scientists spent decades trying to understand how a magnetic field could even function that way. It has rings so dark they reflect barely 2% of the sunlight that strikes them. It has moons that may hold liquid oceans beneath their frozen surfaces, and a cliff face on one of them so tall that you could stack 9 Mount Everests on top of each other and still not reach the summit. It should be dead. According to everything we understood about planetary physics, it should be geologically frozen, internally inert, and scientifically unremarkable. And for 39 years, only one spacecraft has ever visited it. Why does a planet this strange sit so quietly at the edge of our perception, dim and featureless to the naked eye, while the science beneath that pale blue-green surface reframes how we understand the evolution of worlds across the entire galaxy? And what does it mean that we have essentially ignored it, sending humanity's only emissary past it in a single 6-hour window in January 1986, never to return? There is a deeply human irony buried in the discovery of Uranus. It is visible to the naked eye. On a clear, moonless night, far from city lights, you can, if you know exactly where to look, see it as a faint, slightly greenish point of light hanging in the darkness. Ancient observers saw it. They recorded it. They wrote it down in star catalogues stretching back thousands of years. And for every single one of those thousands of years, they assumed it was a star. 22 separate documented observations of Uranus were made before William Herschel formally identified it as a planet. On the 13th of March, 1781, the astronomer John Flamsteed recorded it in 1690, cataloguing it as a star he called 34 Tauri. The French astronomer Pierre-Charles Lemonnier observed it no fewer than 12 times between 1750 and 1769 and still did not recognize what he was looking at. The planet was hiding in plain sight, moving so slowly across the sky, completing one orbit of the Sun every 84.02 Earth years, that its motion against the background stars was imperceptible. Without sustained, careful observation, William Herschel, a German-born musician turned self-taught astronomer living in Bath, England, was the one who finally noticed. He was conducting a systematic survey of the sky with a homemade telescope, a 6.2-inch reflector that he had built himself, grinding the mirror by hand, when he observed a disk that was distinctly not a point of light. Stars, even through a powerful telescope, remain pinpoints. Planets, close enough and large enough, show a tiny but measurable disk. On the night of March 13, Herschel recorded what he initially took to be a comet, noting its unusual appearance. Over the following weeks, as he tracked its movement and established that it followed a circular orbit rather than the elongated path of a comet, he and the astronomical community came to a startling conclusion. This was a planet. A new planet. The first new planet to be discovered in recorded human history. The discovery effectively doubled the known size of the solar system overnight. Uranus orbits the Sun at an average distance of 19 astronomical units, roughly 2.87 billion kilometers from the Sun at its closest approach, and slightly more than 3 billion kilometers at its farthest. Saturn, the previous outermost known planet, sits at just 5 astronomical units. Herschel's telescope had, in a single evening's work, extended our understanding of the solar system's reach by a factor of 2. It is one of the most consequential acts of observation in the history of science, and it was performed by a man who made his living playing the oboe. Herschel initially wanted to name his discovery Georgium Sidus, the Georgian star, in honour of King George III, who subsequently awarded him a royal pension that allowed him to abandon music for astronomy full-time. The international astronomical community was not enthusiastic about naming a planet after the current British monarch, and after decades of debate, the name Uranus, suggested by the German astronomer Johann Elert Bode, gradually took hold. Uranus was the ancient Greek god of the sky, father of Saturn, grandfather of Jupiter, the primordial deity from whom the entire Olympian dynasty descended. It was the first planet in our solar system to be named after a Greek rather than Roman deity, which still makes it technically the odd one out in the naming convention. What Herschel had actually found, though none of the 18th century's finest minds could have known it then, was something categorically different from any planet previously observed. Uranus is not a smaller version of Jupiter or Saturn. It is not a larger version of Earth. It belongs to a class of worlds that we have only recently given a proper name, an ice giant. Not because it is covered in ice in the conventional sense. The surface temperature is cold enough, reaching a minimum of -224 degrees Celsius to freeze most things. But because its interior is dominated not by hydrogen and helium gas, as in Jupiter and Saturn, but by a thick, pressurized, superheated mantle of water, ammonia and methane in exotic states of matter that don't exist anywhere on Earth. The ice in ice giant refers to these compounds which planetary scientists classify as ices in the context of planetary formation. Under the extreme pressures found inside Uranus, water does not freeze and it does not boil. It becomes something in between, a dense, electrically conductive fluid, a slushy supercritical ocean pressing down on a small rocky core with a force that no instrument we have ever built could survive. The atmosphere we can observe, that pale, featureless, cyan-tinted shell, is composed of approximately 83% hydrogen and 15% helium, with about 2.3% methane. It is the methane that gives Uranus its distinctive colour. Methane absorbs red wavelengths of sunlight and reflects blue and green, producing that characteristic blue-green hue that makes the planet look, at first glance, so serenely beautiful in a photograph taken from a billion kilometres away. That serene appearance is a lie of sorts. Wind speeds inside Uranus's atmosphere reach 900 kilometres per hour. The tropopause, the boundary between the lower and upper atmosphere, plunges to 47 Kelvin, which is -226 degrees Celsius, making it the coldest point in the entire solar system. And beneath that placid, featureless surface, physics is doing things we barely understand. There is a question that has hovered over Uranus since the moment we first had the instruments to ask it, and it is a question that took nearly 4 decades to even partially answer. But to understand why that question matters so profoundly, we need to understand what makes Uranus so fundamentally different from every other giant in our solar system. And that story begins, as so many of the best stories in planetary science do, with the planet's almost incomprehensibly strange orientation in space. Stand a spinning top on a table and watch it rotate. Its axis, the invisible line through its centre around which it spins, stands upright, more or less perpendicular to the surface below it. All planets work this way, to varying degrees. Earth's axis tilts at 23.5 degrees from vertical, which is why we have seasons. Mars tilts at 25.2 degrees, giving it seasons similar to our own. Saturn tilts at 26.7 degrees. Even Venus, which rotates almost completely upside down, has an axial tilt of 177.4 degrees, which is geometrically speaking close to zero because Venus is barely spinning relative to vertical. Uranus has an axial tilt of 97.77 degrees. That number deserves a moment to breathe. An axial tilt of 90 degrees would mean a planet spinning on its side, its poles pointing directly toward and away from the Sun during the course of its orbit. Uranus exceeds 90 degrees, which means it is technically rotating in the opposite direction to most other planets, retrograde, while simultaneously lying almost perfectly on its side. Picture a marble rolling along a flat surface, not spinning on its vertical axis, but tumbling forward along its equator. That is Uranus. It does not spin upright and orbit the Sun. It rolls like a billiard ball knocked sideways by some catastrophic impact that happened long before any human being ever looked up at the night sky. The consequences of this orientation are extraordinary and, once you think them through carefully, deeply counterintuitive. Uranus's 84-year orbit means that each of its 4 seasons lasts approximately 21 Earth years. During the course of one Uranian year, the planet's north pole points almost directly at the Sun for 21 years, while the south pole sits in total unbroken darkness. Then, as the planet continues its orbit, the geometry shifts and the equatorial regions receive the most sunlight. And then the south pole swings into perpetual summer, while the north pole endures 21 years of night. The most extreme seasons in the entire solar system, by an enormous margin, occur not on some hypothetical world we've detected from light years away, but right here, in our own solar neighbourhood. When Voyager 2 flew past Uranus on the 24th of January 1986, the South Pole was pointed almost directly at the Sun. The spacecraft arrived during the Uranian summer solstice, and yet, even with one pole baking in continuous sunlight and the other in perpetual darkness, the temperature difference between the two poles was essentially zero. The planet was distributing heat so efficiently. Through circulation mechanisms we still don't fully understand, that the illuminated pole and the freezing pole were within a degree or two of each other in temperature, an entire hemisphere receiving 21 years of continuous sunlight, and barely a trace of the temperature difference you might expect. That is one of the smaller mysteries of Uranus. The larger ones are considerably stranger. The question of why Uranus is tilted at all is one that planetary scientists have wrestled with for decades. The leading explanation, the one that most models find most consistent with the available evidence, is a giant impact. Sometime during the early solar system's first few 100 million years, when the planets were still accreting from the disk of gas and dust surrounding the young Sun, Uranus was struck by a body estimated to have been somewhere between 1 and 3 times the mass of Earth. The impact was not head-on. It struck at an angle, at the precise geometry required to tip a planet nearly onto its side without completely shattering it. Simulations suggest the impactor was probably composed largely of ice, which would have deposited its material into Uranus's outer layers rather than the core. This is, to my mind, one of the most haunting ideas in planetary science. Somewhere in the first 500 million years of the solar system's existence, a world the size of several Earths, a world that might itself have been on a trajectory toward becoming an ice giant, crashed into what would become Uranus, was consumed by it, and in doing so changed everything. It changed the seasons. It changed the orientation of the magnetic field. And, according to one line of thinking, it may have changed the thermal history of the planet in a way that left a fingerprint we have been misreading for the better part of a century. But the giant impact hypothesis, as elegant and satisfying as it is, does not fully explain everything we observe. It does not cleanly explain why the impact failed to leave Uranus rotating much faster, as impacts of that scale typically do. It struggles with the exact distribution of mass we observe in Uranus's moons, which orbit in the equatorial plane tilted along with the planet, suggesting they formed after the tipping event rather than before, which is consistent with a giant impact, but not perfectly so. In 2022, a separate team of researchers proposed an alternative. A massive moon, early in Uranus's history, spiraled inward under tidal forces, and as it fell, gradually torqued the planet's rotation axis over millions of years before being consumed. Computer simulations showed this was physically possible, though the initial tilt that seeded the process still requires explanation. Here is the problem that sits at the centre of everything else. We have one data point. One spacecraft visited Uranus, spent 6 hours making close observations and left. The magnetic field measurements Voyager 2 collected during that single flyby remain the only in situ measurements of Uranus's magnetic field that human beings have ever obtained. Everything else we know, or think we know, has been derived from telescope observations across vast distances, and what Voyager 2 found in those 6 hours was deeply unusual. So unusual that planetary scientists spent the next 3 decades arguing about whether the measurements could possibly be correct. The magnetic field of Uranus is unlike anything else in the solar system, and understanding why requires understanding something about how magnetic fields on planets are supposed to work. and why Uranus appears to be doing something entirely different. On Earth, the magnetic field is generated by motion inside our planet's liquid iron outer core, a process called magnetohydrodynamic convection, in which the circulation of electrically conductive molten metal around the solid inner core generates electrical currents, and those currents generate a magnetic field. The axis of that field is tilted roughly 11 degrees from Earth's rotational axis, not a perfect alignment, but close enough that a compass points approximately north with a small but measurable deviation that navigators have accounted for centuries. Jupiter's magnetic field is tilted only about 10 degrees from its rotational axis. Saturn's is almost perfectly aligned with a tilt of less than 1 degree. These are planetary magnetic fields behaving as planetary magnetic fields should behave. Uranus's magnetic field is tilted 59 degrees from its rotational axis, and it doesn't originate from anywhere near the planet's centre. It is offset, displaced so far from the planet's geometric centre that a dipole model of the field doesn't even approximately describe what's actually there. Instead, Uranus's magnetic field is better described as a quadrupole or higher-order multipole, a complex, tangled web of competing magnetic regions that can only be explained if the field is being generated not deep in the core, as on Earth, but somewhere much shallower in the icy mantle layer. The electrically conductive water-ammonia mixture at high pressure is the most likely candidate for the dynamo source, but exactly how that works, what drives the convection patterns inside a supercritical fluid ocean that is itself spinning sideways, remains one of the most unresolved questions in planetary physics. The consequences of this malformed magnetic field are cascading and deeply strange. Because the magnetic axis is so dramatically offset from the rotation axis, as Uranus rotates every 17 hours and 14 minutes, the magnetic field tumbles through space, not oriented consistently with the planet's spin, but whipping around it like a lasso thrown by someone who has never used a lasso before. This creates a magnetosphere, the region of space controlled by the planet's magnetic influence, that undergoes something researchers have called, without much exaggeration, a switch-like behaviour. As Uranus rotates and its misaligned magnetic field sweeps through different orientations relative to the solar wind, the magnetosphere alternately opens and closes. When the geometry is right, the solar wind can penetrate directly into the magnetosphere, connecting with field lines in a process called magnetic reconnection. When the geometry is wrong, the magnetosphere seals shut. This open-close cycling happens once per Uranian rotation, every 17 hours and 14 minutes, making Uranus's magnetosphere unlike anything else we have observed in any planetary system we have studied. I find this genuinely extraordinary, and not only for its scientific novelty. The implications of a switching magnetosphere for the habitability conditions on Uranus's moons, which we will come to, are significant in ways that planetary scientists are only beginning to quantify. A magnetosphere that regularly opens and allows the solar wind to flood in means regular particle bombardment of the moons orbiting inside it. It means energetic charged particles being accelerated toward those worlds on a 17-hour cycle, potentially stripping their surfaces of lighter molecules, driving chemistry in their upper atmospheres, and delivering energy to subsurface environments in ways we haven't begun to model. The moons of Uranus sit inside this magnetic cyclone, and what that does to their interiors and their potential habitability is, as of this moment, entirely unknown. There is something else that Voyager 2 found, something that was recorded in the data, and then, to some extent, set aside as a curiosity because the context to interpret it fully didn't yet exist. The radiation belts of Uranus, the zones of energetically charged particles trapped by the magnetic field, analogous to Earth's Van Allen belts, were anomalously weak. Given the strength of the magnetic field, models predicted robust, dense radiation belts. What Voyager 2 measured was substantially thinner than expected. Something was absorbing the charged particles, sweeping them up before they could accumulate. The most likely culprits are Uranus's rings and inner moons, acting as particle sinks, but the exact mechanism and what that means for the particle environment across the entire Uranian system has been a source of debate in a series of papers published as recently as 2024, building on that single 1986 dataset that remains, nearly 4 decades later, the only close-up measurement we have. This is, I think, one of the more remarkable facts about Uranus in the context of modern planetary science. We have mapped the surface of Mars down to the resolution of a dining table. We have sampled comets. We have landed on Titan. We have flown a helicopter through the Martian atmosphere. And yet, for the 7th planet in our own solar system, a world 4 times wider than Earth, containing 63 Earths' worth of volume, our entire dataset of close-range magnetic field measurements consists of 6 hours of data collected by a spacecraft that launched in 1977 and is now travelling through interstellar space. That is the entirety of what we know from direct observation. Everything else is inference, modelling, and educated extrapolation. But within that handful of extraordinary mysteries, the tilt, the broken magnetic field, the cycling magnetosphere, there is one problem that stood above all others for nearly 40 years. One problem that seemed to suggest that Uranus was not merely strange, but fundamentally different from every other giant planet in existence. One problem that, if it had been true, would have required a complete rethinking of how planets form and how they evolve over billions of years. Scientists called it the cold planet problem, and until 2025 it had no answer. Every giant planet in our solar system radiates more heat than it receives from the Sun. This is not a coincidence or an anomaly, it is a fundamental consequence of planetary formation. When a planet forms, the gravitational collapse of its constituent material releases enormous amounts of energy. Rocky planets lose this primordial heat relatively quickly because rock conducts heat efficiently, and the surface-to-volume ratio is large enough for smaller worlds to cool on timescales of billions of years. Giant planets, however, are so massive and so thermally insulated by their thick atmospheres that they retain a substantial fraction of their formation energy across the entire age of the solar system, and radiate it slowly into space as infrared excess, emitting more heat than they receive from the Sun. Even now, 4.5 billion years after their formation, Jupiter radiates 1.67 times more energy than it receives from the Sun. Saturn radiates approximately 1.8 times more. Neptune, the most distant giant, radiates 6 times more energy than the Sun delivers to it at that range. These figures are consistent with theoretical models of giant planet formation and cooling. They are exactly what you would expect, given the physics. When Voyager 2 flew past Uranus in 1986, it carried instruments designed to measure the planet's energy balance. The ratio between sunlight absorbed and heat radiated back into space. The measurement it returned was, to put it mildly, bewildering. Uranus appeared to radiate essentially no excess heat. Its internal heat flux, according to the Voyager data, was indistinguishable from zero. The planet appeared to be in thermal equilibrium with the Sun, absorbing as much energy as it emitted, with no detectable contribution from internal primordial heat. For a planet of Uranus's size and mass, this made no physical sense. The models said there should be a detectable heat excess. The data said there was none, and for 39 years, no one could explain the discrepancy. The cold planet problem, as it became known, generated a remarkable proliferation of hypotheses, some of them quite creative. The most widely discussed early explanation involved the giant impact that tipped Uranus on its side. The argument went like this: the same catastrophic collision that tilted the planet also mixed the interior violently enough to destroy the temperature stratification that allows heat to rise from the core to the surface. Instead, the interior of Uranus became stably stratified, layered like an oil and water system in which denser, hotter material sat beneath lighter, cooler material without mixing. In a stably stratified interior, convection, the mechanism by which interior heat reaches the surface, is suppressed. The heat from formation became trapped deep inside the planet, unable to escape, leaving the outer layers cold and the measurements of internal heat flux, suggesting a planet that had somehow already lost all its primordial warmth. This hypothesis had a certain elegant brutality to it. The same event that made Uranus strange also imprisoned its heat. The planet had been knocked onto its side and sealed like a thermos flask, its warmth locked inside, invisible to every instrument we could deploy from the outside. And for decades, this explanation, or variations of it, was the best answer the community had. But it was always a slightly unsatisfying answer, because it raised a further question that no one could cleanly resolve. If Uranus's interior was stably stratified and its heat was trapped, how did it still manage to generate the powerful weather systems we observed? Wind speeds of 900 kilometers per hour require energy. Persistent storms require energy. The atmospheric dynamics of Uranus were clearly not those of a dead, inert planet. Something was driving convection, at least in the outer layers. But what? Then came 2025. A team of researchers led by Jinyue Wang at the University of Houston, working in collaboration with planetary scientists at institutions around the world, and corroborated independently by a separate group led by Professor Patrick Irwin at the University of Oxford, published results in geophysical research letters that changed the picture, using not the snapshot Voyager data from 1986, but decades of accumulated spacecraft and telescope observations, combined with sophisticated computer modelling techniques that had only recently become computationally tractable. They found something that the Voyager instruments had missed or could not resolve. Uranus does emit internal heat. The planet radiates approximately 12.5% more energy than it receives from the Sun. The internal heat flux is 0.078 plus more 0.018 watts per square metre, 12.5%. That is a real number, a measurable excess. The cold planet problem, which had defined our understanding of Uranus for nearly 4 decades, was not a reflection of reality. It was a measurement artifact, a consequence of the limited precision available to a 1977-era spacecraft, making a single pass through a system that, as we now know, also varies seasonally in its energy output. Uranus's long seasons and its elliptical orbit create fluctuations in the energy budget that a brief flyby could not capture with sufficient fidelity. This is, I will admit, one of those moments in science where I had to sit with the result before I could fully process it. Not because the measurement is dramatically large, 5% is modest compared to Jupiter's 67% excess, or Neptune's 160%. Uranus still has the weakest internal heat output of any giant planet in the solar system by a significant margin, but it has some, and that changes the nature of the problem. The question is no longer why does Uranus have no internal heat? A question that required exotic explanations for an apparent absence. The question is now, why does Uranus have so much less internal heat than the other giants? And that is a subtler, richer, more productive question. The leading hypothesis remains the stratified interior, possibly caused by the ancient giant impact. But the impact cannot have been so perfectly catastrophic as to trap all of the heat. Only most of it. The interior must have some convection reaching the surface, just far less efficient than in Jupiter or Neptune. What creates that difference in efficiency? Is it the composition of the icy mantle? Is it something about the geometry of the magnetic field, which is itself generated somewhere in that same interior, and which may influence convective flow? Is it the legacy of whatever body struck Uranus all those billions of years ago, depositing material in layers that altered the interior structure permanently? These questions now have a sharper focus, and they will not be answerable from Earth. They will require a spacecraft, one that has not yet been launched, one that remains, as of mid-2026, a concept on a drawing board, fighting for funding in an era of tightened budgets and competing priorities. But first, to understand what we stand to learn, we need to understand what one extraordinary human being discovered almost entirely by accident, flying through the darkness over a remote ocean in a converted military aircraft, waiting for a star to disappear. The night of March 10, 1977, was not supposed to be about rings. Jim Elliot was not flying above the South Indian Ocean in a converted Lockheed C-141 Starlifter, the Gerald P. Kuiper Airborne Observatory, in order to discover that Uranus had a ring system. No one, that night, thought Uranus had a ring system. The whole point of the exercise was to measure something else entirely. Uranus was due to pass in front of a distant star, a stellar occultation, an event in which a planet moves directly between a star and the observer, temporarily blocking the star's light. By watching precisely how the starlight dims and brightens as the planet's edge passes across it, you can probe the planet's atmosphere with extraordinary sensitivity. The timing and rate of the dimming tells you about atmospheric density, pressure and composition. It is, as Elliot well knew, one of the most powerful observational tools available to planetary astronomers who cannot send a spacecraft to make direct measurements. He had pioneered the technique, and he and his team from Cornell University were airborne that night, with a high-altitude telescope mounted in the aircraft's fuselage, specifically to capture the Uranus star geometry and extract atmospheric data. Because the precise timing of the occultation was uncertain by about 40 minutes, Elliot instructed his team to begin observing approximately an hour before the expected event. That caution, that professionalism, that meticulous preparation changed history. About 40 minutes before Uranus itself reached the starlight dipped, briefly. A sharp, clean reduction in brightness, lasting only a few seconds, then recovering completely. Then it dipped again, and again. 5 distinct dips in the starlight, spread across about half an hour before Uranus moved in front of the star and the expected main occultation began. The team noted the anomalies, but continued the observation. Then Uranus passed across the star, the main event was recorded, and as the star re-emerged on the other side of the planet, the starlight dipped again, 5 more times, in a pattern almost perfectly mirroring the dips observed before the planet arrived. The symmetry was the key. If the dips before and after the main occultation had been random or asymmetric, they could have been instrument noise, atmospheric scintillation, a passing cloud. But a pattern of 5 dips before and 5 dips after, on both sides of the planet in nearly symmetric geometry, that was not noise, that was structure. Orbiting structure, rings, Elliot knew, within hours, what he had found. The paper announcing the discovery of a ring system around Uranus was published in Nature in May 1977. 9 distinct rings were ultimately identified from the data, the innermost ring designated 6, and the outermost and widest designated epsilon, for the Greek letter that would become the name most associated with Uranus's ring system. These were rings unlike Saturn's. Saturn's rings are broad, luminous, composed of ice particles, ranging in size from grains of sand to boulders several meters across, reflecting sunlight so brilliantly that they are visible from Earth through a modest backyard telescope. Uranus's rings are narrow. The epsilon ring, the widest, spans only about 100 kilometers in width, and dark, made of material that absorbs nearly all incident light, reflecting only about 2%. They were invisible to any telescope before the moment Elliot's instruments detected their shadow on a background star. I want to stay with Jim Elliot for a moment, because his story is one that I think deserves more attention than it typically receives. He was, in the accounts of everyone who knew him, an unusually complete human being, not just a scientist of the first rank, but someone who treated science as a fundamentally communal and moral enterprise. He was, by every account, one of the great advocates for women in astronomy during a period when that advocacy cost something, when it was not the institutional default it is supposed to be today, but a genuine act of will and support in environments that often discouraged women's participation. More than half of the students who spoke at a scientific celebration held in his honour at MIT in 2010, called the Gymboree by his colleagues, were women. That is not an accident. That is the product of a career-long commitment to something that went beyond the technical. He was known for carrying white index cards in his pocket at all times. His students remembered him never caught without one, always ready to sketch a diagram, write down a calculation, capture a thought before it escaped. he would send his graduate students out to do observations on their own, with, in the words of people who worked with him, utter trust that they could do the research themselves. That trust, the willingness to give young scientists ownership of their work, to resist the temptation to hold the reins, is rarer than it should be in academic science, and its ripple effects extend far beyond any single research paper. After the Uranus ring's discovery, Elliot continued applying the stellar occultation technique to the outer solar system with remarkable productivity. In 1988, he and his team observed Pluto as it passed in front of a star. The star's light did not disappear abruptly, as it would have if Pluto had no atmosphere. Instead, it dimmed gradually, a gradation that could only be explained if something gaseous, thin but real, surrounded the tiny world. Elliot and his colleagues had discovered that Pluto has an atmosphere. It is a discovery that fundamentally changed our understanding of the Kuiper Belt's most famous resident long before the New Horizons spacecraft arrived in 2015 and confirmed everything in extraordinary detail. Jim Elliot died on the 3rd of March 2011 from complications arising from cancer. He was 67 years old. At the time of his death, he had observations of Pluto planned for June of that year. Observations that his colleagues and students carried out in his name. The image that stays with me is this one, a scientist who spent a career watching stars blink out behind distant worlds, whose last intellectual act was to ensure that the next occultation would be covered, that the data would be collected, that the work would continue. He died, as he had lived, making sure that someone was watching. The rings he discovered that night over the Indian Ocean have since been imaged directly by Voyager 2, by the Hubble Space Telescope, and in extraordinary detail by the James Webb Space Telescope, which in 2023 revealed not only the 13 rings known at that point, but also detected the innermost and most tenuous ring, designated Zeta, so faint it had previously eluded direct imaging. The rings appear to be geologically young, the material too dark and absorbing to have survived billions of years of space weathering without being replenished or refreshed, which suggests either ongoing input from the surrounding moons or some dynamic process that continuously renews the ring material. That question, where does the ring material come from, and what keeps these extraordinarily narrow structures from spreading and dispersing over millions of years, has not been answered. It sits alongside the other open questions about Uranus, waiting for a spacecraft that will, someday, arrive, but the rings of Uranus, extraordinary as they are not the most scientifically significant discovery that has emerged from the Uranian system in recent years. In August 2025, the James Webb Space Telescope detected a new moon orbiting Uranus, designated S2025U1, bringing the total known moon count to 29, and in doing so reminded the scientific community that this system is still yielding surprises without a single spacecraft having visited it since 1986. More consequential still is what we have come to understand, in the years since Voyager 2, about the extraordinary moons it did photograph. Because if what current models suggest is correct, the moons of Uranus may be among the most scientifically significant worlds in the entire solar system for one reason above all others. They may be ocean worlds. We have spent decades building a conceptual framework for where liquid water, and therefore potentially life, can exist in the outer solar system. The framework centres on tidal heating, the gravitational kneading of a moon by its host planet, which generates friction in the moon's interior, which generates heat, which keeps subsurface water liquid beneath the frozen crust. Europa, orbiting Jupiter in a gravitational tug-of-war with Io and Ganymede, is squeezed and stretched so vigorously that its subsurface ocean is almost certainly liquid and potentially habitable. Enceladus, moon of Saturn, is so vigorously tidally heated that it erupts plumes of water vapour and ice particles from its south pole. We have flown through those plumes with the Cassini spacecraft and detected organic molecules, molecular hydrogen, and the chemical conditions consistent with hydrothermal vents on the ocean floor. Uranus, sitting nearly 3 billion kilometres from the Sun, was long assumed to be too cold and too distant for any of its moons to host liquid water. The Sun delivers so little energy at that distance, about 1/400th of what it delivers to Earth, that without substantial internal heat sources, the Moon should be frozen solid all the way through. Tidal heating at Uranus was expected to be weak. The planet's moons orbit in near-circular paths with low eccentricities, and it is eccentricity, the elongation of an orbit, that drives tidal heating most effectively. Without the orbital resonances that keep Europa and Enceladus in their gravitationally turbulent dance, the Uranian moons seemed destined to be cold, geologically dead ice balls. Voyager 2 photographed them briefly as it swept through the system, and what it found was not entirely consistent with the frozen dead narrative. Miranda, smallest of the 5 major moons at just 471.6 kilometers in diameter, should, by all the models available in 1986, have been a simple, undifferentiated sphere of mixed ice and rock. What Voyager 2 revealed was one of the most geologically chaotic surfaces in the solar system. Miranda's terrain is a collision of completely incompatible geological histories, ancient, heavily cratered plains sitting directly adjacent to regions of extraordinary tectonic complexity called coronae, roughly rectangular or oval regions of parallel ridges and valleys that look like they were carved by some internal force pressing upward through the crust. The most dramatic feature of all is Verona Rupes, a cliff face so tall, approximately 20 kilometers from base to rim, that it qualifies as the highest known cliff in the entire solar system. From the base of Verona Rupes, the rim would be invisible below the horizon of the curved moon. An object dropped from the top would, in Miranda's low gravity, take approximately 12 minutes to reach the bottom. Scientists debated for years what had produced Miranda's extraordinary terrain. The most popular early explanation was catastrophic. Miranda had been shattered by an ancient impact and reassembled from its own fragments, with incompatible sections of former interior landing adjacent to sections of former crust in the reconstituted body. The problem with this explanation is that it requires a very specific sequence of impacts and reassemblies that grows increasingly improbable under close scrutiny. More recent modelling has suggested that Miranda may have undergone tidal resonance, a period in its past when its orbital geometry aligned with another moon, creating temporarily enhanced tidal heating that drove internal convection and resurfacing before the resonance dissipated. And there is more. In October 2024, researchers at the Johns Hopkins University Applied Physics Laboratory published a study suggesting that Miranda may have, or may have had, a subsurface liquid water ocean. The modelling showed that even with modest internal heat sources, radiogenic decay from rocky material in the core, Miranda's icy shell could potentially insulate an interior warm enough to maintain liquid water beneath the surface for extended periods. This would make Miranda a potential ocean world, tiny, frozen-looking from the outside, and potentially harbouring a liquid realm beneath the ice. Miranda is not alone in this. The same 2024 analysis, building on work published the previous year examining all 5 major Uranian moons, found that Ariel, Umbriel, Titania and Oberon may also retain subsurface oceans. The 4 largest moons, Titania and Oberon, are each larger than 1/500 kilometers in diameter, have sufficient rocky material in their interiors to generate radiogenic heat from the decay of radioactive isotopes, uranium-238, thorium-232 and potassium-40, the long-lived heat sources that have kept Earth's interior warm across the entire age of the solar system. For larger moons, this radiogenic heating might be sufficient to maintain liquid water at the rock-ice interface, deep beneath the frozen surface. For Titania and Oberon specifically, the rocky mantle might be releasing heat directly into this internal ocean, potentially creating the thermal gradients necessary for the chemistry that, in an ocean hydrothermal vent on Earth, has been found to support remarkable ecosystems. I want to be precise here, because precision matters in this particular conversation. Saying that the moons of Uranus may harbour subsurface oceans is not the same as saying they harbour life. The conditions for life, liquid water, Energy sources, appropriate chemistry, are necessary but not sufficient. We do not know what the chemistry of a Uranian moon's interior ocean looks like. We do not know whether there are hydrothermal vents. We do not know whether the rock-ice interface has the right chemical gradients to drive prebiotic chemistry. What we know is that the physical conditions that have, on Earth, produced the environments most hospitable to life may be present, quietly, invisibly, inside worlds that we have never looked at carefully and that sit 87 billion kilometers from the Sun in a solar system neighborhood we have visited exactly once. The Uranian system could be harboring as many as 5 ocean worlds, each with its own geological history, each with its own potential for chemistry that matters. Europa Clipper was launched in October 2024 to investigate a single moon of Jupiter. Cassini gave us Enceladus. The moons of Uranus have never had their own mission. They have had 6 hours of a 1986 flyby. That asymmetry between what we have found and what we have not yet looked for is one that the planetary science community has increasingly begun to argue cannot be sustained, which raises the question that stands at the very heart of where Uranian science is heading and why the planetary community has placed it at the top of a priority list that will shape the trajectory of exploration for the next 2 decades. The stakes are no longer local. They are not merely about Uranus itself, because the single most important reason to understand Uranus is not what it can tell us about our solar system, it is what it can tell us about every other solar system in the galaxy. Here is a number that I believe deserves considerably more public attention than it receives. Of the more than 5,700 confirmed exoplanets catalogued as of mid-2026, the most common type by a substantial margin is a planet with a radius somewhere between 1.5 and 4 times that of Earth. Too large to be a rocky world like our own, too small to be a gas giant like Jupiter, and with a composition that theoretical models suggest is dominated not by rock or by hydrogen and helium, but by water, ammonia, and other volatile compounds in their exotic high-pressure states. In other words, ice giants. Uranus-class worlds, the most common type of planet in the observable universe, appears to be, broadly speaking, Uranus, and yet Uranus, our single, close, accessible example of this overwhelmingly dominant planetary category, has received 1 spacecraft visit in the entire history of human spaceflight. This is, in the language of scientific resource allocation, an extraordinary mismatch. We have sent 6 spacecraft to Mars. We have orbited Jupiter with Galileo and Juno. We have sent the Cassini spacecraft to spend 13 years in orbit around Saturn, producing a dataset that will take planetary scientist generations to fully process. We have successfully landed on Titan, the only moon with a substantial atmosphere, dropped a probe into Venus's acid clouds, and sent New Horizons to the Kuiper Belt. For the most common type of planet in the galaxy, we have managed a 6-hour flyby. The consequences of this neglect, I think neglect is the right word, extend across multiple dimensions of planetary science simultaneously. Consider the question of ice giant interiors, the composition of Uranus's interior, the exact ratios of water to ammonia to methane, the phase transitions between the icy mantle and the hypothetical rocky core, the nature of the electrically conductive layer that generates the magnetic field is almost entirely unknown. We have compositional data from the upper atmosphere, which is mostly hydrogen and helium. We have gravity measurements from Voyager 2, which constrain the bulk density. Everything in between is inference. Models of Uranus's interior have proliferated in the scientific literature, each consistent with the limited observational constraints we possess, and each making different predictions about the internal structure. A 2024 paper in Astronomy and Astrophysics reviewed the current state of interior models and concluded, with admirable directness, that the data we have is insufficient to distinguish between fundamentally different interior architectures. Whether Uranus has a distinct rocky core or a gradual compositional gradient, whether its icy mantle is uniform or layered, whether the magnetic field generating region is a thin shell or a thick layer, This uncertainty matters for exoplanet science in a concrete, immediate way. When astronomers detect an exoplanet with a radius of 2.5 Earth radii and a mass of 12 Earth masses, which is a very typical Uranus-like exoplanet by current catalogues, they need to know what that planet is likely made of, how its interior is structured, and how its magnetic field might influence its habitability and atmospheric evolution. To answer those questions with any confidence, they need a detailed physical model, and to build a detailed physical model, they need data from an actual ice giant interior. Uranus is the only ice giant within reach of a spacecraft in any human lifetime. If we want to understand the most common type of planet in the galaxy, we must understand Uranus. There is no substitute and there is no shortcut. The problem compounds when you consider atmospheric noble gas abundances. One of the deepest questions in planetary formation is, where did the giant planets form? And how did they migrate from their formation locations to their current positions? The NICE model, the most widely accepted theoretical framework for the early solar system's dynamical history, suggests that the giant planets formed much closer to the Sun and then underwent a period of dramatic gravitational reshuffling in the first 500 million years or so of solar system history. In this model, Uranus and Neptune may have actually formed in each other's places, swapping positions as they migrated outward. The noble gases in a planet's atmosphere, helium, neon, argon, krypton, xenon, are chemically inert and do not participate in reactions with other atmospheric species. This means their abundances in a planetary atmosphere are a direct record of the composition of the material from which the planet formed and the temperature of the region where it formed. They are, in effect, a barcode for the planet's birthplace. The problem is that noble gases cannot be detected remotely. They do not emit or absorb light at wavelengths accessible to telescopes. The only way to measure noble gas abundances in a planet's atmosphere is to send an atmospheric probe, a hardened descent vehicle, directly into the atmosphere and sample it in situ. Jupiter's noble gas abundances were measured this way by the Galileo atmospheric probe in 1995. Saturn's, remarkably, have never been directly measured. Uranus's have never been measured. Neptune's have never been measured. The birthplace question: where did the ice giants form, and did they swap positions in a gravitational reshuffling that also sent a barrage of comets and asteroids toward the inner planets, potentially delivering the building blocks of life to early Earth? Cannot be answered without sending a probe into the atmosphere of at least one of them. There is also the matter of how Uranus's magnetic field actually works. Everything we know about the Uranian magnetic field comes from 6 hours of data collected in January 1986. In those 6 hours, Voyager 2 measured the field's strength, its orientation, and its spatial structure at a single point in time. The magnetic field of a planet is not static. It evolves, it fluctuates, it responds to changes in the interior. Earth's magnetic field has reversed polarity multiple times in geological history. We have no idea whether Uranus's magnetic field has changed since 1986, whether it is strengthening or weakening, whether the internal dynamics that generate it are in a stable configuration or an evolving one. A 2024 study published in Nature Astronomy using the Voyager 2 data in combination with modelling of particle dynamics in the magnetosphere found hints that the magnetospheric state Voyager observed may have been unusually compressed, that the spacecraft may have arrived during a period of elevated solar wind pressure, potentially catching the magnetosphere in a temporary state rather than its typical configuration. If that is correct, then even the one measurement we have may not be representative of Uranus's normal magnetic behaviour. We are, in a very real sense, trying to understand the magnetic personality of a world from a single photograph taken under unusual lighting conditions. And then there is the question that, to my mind, is the most provocative open problem in ice giant science, and one that has only gained urgency in the last several years. The question of what happens to carbon inside Uranus at the temperatures and pressures found in Uranus's interior, temperatures of several thousand Kelvin, pressures reaching millions of atmospheres. The methane that constitutes roughly 2–3% of the planet's upper atmosphere would be chemically destroyed. The carbon and hydrogen atoms of methane molecules separate under extreme compression. The hydrogen rises toward the outer layers. The carbon, under the right conditions, does something remarkable. It forms diamonds. Not diamond dust, not microscopic crystal fragments, but potentially large, dense diamonds that form under the crushing pressure of the deep interior, and then sink, like stones falling through water, down toward the rocky core. Along the way they melt. Diamond has a higher melting point than most substances, but not at pressures of millions of atmospheres. At those pressures, the phase diagram of carbon predicts regions where diamond becomes liquid. A diamond rain of liquid carbon that may surround Uranus's rocky core in an ocean of the hardest natural material on Earth, liquefied by pressure and flowing like water around the planet's centre. Laboratory experiments at the SLAC National Accelerator Laboratory, using high-powered lasers to compress tiny samples of plastic, a proxy for the carbon-hydrogen mixtures found in ice giant interiors, to pressures comparable to those inside Uranus and Neptune, have produced direct evidence that diamond nanocrystals form under these conditions, and that the process occurs at lower temperatures and pressures than previously believed. A 2024 paper from that team found that the addition of oxygen, as would be present in the water of a real planetary interior, lowers the threshold for diamond formation even further. This means that diamond precipitation is not a hypothetical exotic process. It may be happening inside Uranus right now as you read or listen to this. Continuously, billions of tons of carbon sinking through the planet's interior in a rain that has been falling for 4.5 billion years. That diamond rain may incidentally help explain the magnetic field anomaly. As the diamonds sink and the surrounding fluid flows upward in compensation, the convective dynamics of the interior are altered. The patterns of fluid flow that drive the magnetic dynamo are shaped by this continuous carbon precipitation. It is a strikingly beautiful physical picture. Planet whose magnetic field is partly written in the language of diamonds sinking through a pressurized sea, and it is, as yet, entirely unconfirmed. The experiments tell us the process is physically possible. Only measurements from inside a Uranus-bound mission would allow us to test whether it is actually occurring. All of these threads, the uncertain interior, the broken magnetic field, the ocean worlds and its moons, the atmospheric noble gases, the diamond rain, converge on a single, pressing, increasingly urgent conclusion. We need to go back to Uranus. And we may finally be close enough to doing so to see the mission on the horizon, even if the horizon remains frustratingly distant. In 2022, the National Academies of Sciences, Engineering and Medicine published the Planetary Science Decadal Survey for 2023 to 2032, the comprehensive, community-driven prioritization document that sets the direction of NASA's planetary science program for a decade. The survey designated one mission the highest priority flagship-class effort of the decade, not a Mars sample return cache retrieval, not a return to the outer solar system ice shells of Enceladus or Europa, though those missions featured prominently. The highest priority flagship mission recommended by the planetary science community was the Uranus Orbiter and Probe. This is a significant moment in the history of planetary exploration. The Uranus Orbiter and Probe, known by the acronym UOP, is not a new idea, but the Decadal Survey's elevation of it to the very top of NASA's flagship priority list represents a clear statement by the scientific community that Uranus has been neglected for too long, and that the neglect is no longer scientifically acceptable. The mission concept that the Decadal Survey evaluated carries a cost estimate of approximately $2.15 billion in 2025 currency. Phase A through D, including launch vehicle, comparable in scale and ambition to the Cassini mission at Saturn, which returned science that justified every dollar. The architecture of the proposed mission is elegant in its scope. The spacecraft would launch in a window centered around the June 2031 period to take advantage of a Jupiter gravity assist. a gravitational slingshot maneuver that uses Jupiter's enormous mass to redirect and accelerate the spacecraft without burning additional fuel, reducing the transit time to Uranus from what would otherwise be an unacceptably long direct transfer. With the gravity assist, the travel time is projected at approximately 12 years, with arrival in the mid-40s. The spacecraft would then spend several years in orbit around Uranus, making comprehensive measurements of the magnetic field, the interior through gravity mapping, the atmospheric composition and dynamics, the rings, and the system of moons. Among the most scientifically critical elements of the mission is the atmospheric probe, a hardened descent vehicle that would be released from the main spacecraft and plunge into Uranus's atmosphere, surviving for as long as possible while transmitting data on temperature, pressure, wind, and, crucially, noble gas abundances up through the cloud layers before being crushed by the increasing pressure below. There is, however, a complication that has cast a shadow over the mission's timeline. In 2023, NASA announced that its production of plutonium-238, the radioactive isotope used to fuel radioisotope thermoelectric generators, the RTGs that power spacecraft operating too far from the Sun for solar panels to be practical, was insufficient to support a 2031 or 2032 launch on the originally envisioned schedule. At Uranus's distance, solar power is approximately 1/400th of what is available near Earth. The mission requires RTGs, and RTG production at the scale required for a flagship mission had fallen behind. A revised assessment projected that a mid to late 2030s launch might be more realistic. In the 2026 appropriations cycle, the Uranus orbiter and probe received $100 million for a preliminary study, a meaningful but modest investment that keeps the mission alive on paper, while the broader questions of budget and schedule remain unresolved. The planetary science community is watching carefully. Every year of delay in the launch pushes the arrival date correspondingly further into the future. If the mission slips from a 2031 launch to a 2037 or 2038 launch, the arrival at Uranus moves from the mid-2040s to the early 2050s. The scientists who would execute that mission, receive the data, and spend years processing and interpreting it are, in many cases, graduate students today. Some of them have not yet entered graduate school. The multi-generational nature of outer solar system exploration is not a rhetorical flourish. It is the literal arithmetic of the distances involved. China's space program, meanwhile, has proposed that Tianwen-4, a mission currently in planning that is primarily a mission to Jupiter, include a subprobe that would fly past Uranus. This would be a flyby, not an orbital mission, and it would provide only a limited dataset compared to what an orbiter could achieve. But it would be the first close-range observation of Uranus since 1986, and it would arrive in a timescale considerably more compressed than any Western mission. The prospect of a Chinese flyby of Uranus in the 2030s, before NASA has launched its flagship orbiter, adds a competitive dimension to the urgency that the planetary science community has increasingly acknowledged. There is also the James Webb Space Telescope, which has already demonstrated that it can contribute meaningfully to Uranian science from its position in space. The JWST in January 25 captured the first dataset to continuously observe a full rotation of Uranus from a single instrument, an ESA-WOBI time-lapse that revealed the planet's atmospheric dynamics across a complete 17-hour rotation in unprecedented infrared detail. The telescope's 2023 near-infrared images of Uranus captured the Zeta Ring, the storm systems near the polar cap boundary, and several of the planet's moons simultaneously in a single frame. The JWST's ionospheric measurements published in 2025 confirmed a long-term cooling trend in Uranus's upper atmosphere, a temperature of 426 Kelvin, and revealed for the first time the vertical structure of the ionosphere, the charged particle layer above the neutral atmosphere. These are genuine advances. They are not substitutes for in situ measurements, but they have substantially sharpened the scientific questions that a dedicated mission would need to answer. A 20-year Hubble Space Telescope study of Uranus, published in April 2025, similarly revealed previously undetected changes in the planet's atmospheric appearance across 2 full decades of observation. Changes in the polar cap's extent and brightness, variations in cloud patterns and storm activity, and asymmetries in the planet's appearance between its 2 hemispheres that have evolved as Uranus has moved from its 2007 equinox, when the rings were edge-on to both Sun and Earth, briefly revealing new ring structures, toward the northern summer solstice that will arrive in the mid-2030s. We are watching a planet change, in real time with telescopes that were not designed to watch it. And the changes are raising questions that only a spacecraft in orbit can answer. What the mission would find, if and when it arrives, is impossible to predict with certainty. That is precisely the point. Every time humanity has sent a spacecraft to a world it had not previously visited closely, the discoveries have restructured the questions rather than simply answering them. The Galileo spacecraft at Jupiter found a completely unexpected active volcanic world in Io, not a dead moon, but the most geologically active body in the solar system. Cassini at Saturn found Enceladus erupting water into space, a possibility that had not been seriously considered before the mission arrived. New Horizons at Pluto found an active nitrogen ice plain, a subsurface ocean, a hydrocarbon haze in the atmosphere, and a geological complexity that had been predicted by almost no one. The history of solar system exploration is a record of reality exceeding imagination. Again and again, wherever we have looked carefully enough, Uranus has, by the objective standards of the available evidence, at least as much potential for surprise as any of those worlds. It has a magnetic field we don't understand, generated by a mechanism we can only hypothesize. It has an interior that may contain liquid diamonds surrounding a rocky core. It may have up to 5 ocean worlds in orbit around it, each with its own geological history. It has a ring system that should not maintain its structure on geological timescales, but has persisted anyway. It has an axial tilt that still lacks a definitive explanation. It has now been confirmed to have more internal heat than it appeared to for 4 decades, which reshapes every model we have built of its thermal evolution. And in August 2025, the JWST found it had a moon we did not know about. A planet that keeps yielding surprises to distant telescopes is a planet that has considerably more to show a spacecraft that actually arrives. There is something in the geometry of Uranus that I cannot stop thinking about. The planet rolls through space on its side. One pole pointed toward the Sun, one pole pointed away, the equatorial plane tilted so far toward vertical that it more or less defines the orbital plane itself. And for 21 years at a time, the pole in sunlight is bathed in continuous light, while the pole in darkness never sees the sun. 21 years of day, 21 years of night, back and forth endlessly, across an 84-year year that has repeated for 4.5 billion orbits. The planet doesn't know this is strange. It simply is what it is. I find in this geometry a kind of unexpected metaphor for the experience of scientific knowledge itself. There are things we can see, things turned toward us, illuminated, measured, and catalogued with a precision our instruments allow. And there are things turned away from us, in the dark, unexplored, real but unmeasured, waiting with a patience that has nothing to do with patience, because they have no capacity for impatience. Uranus has been there for 4.5 billion years. It will be there for billions more. The urgency is ours, not the universe's. That urgency, I think, is worth naming directly. The Uranian system contains mysteries that are not merely scientifically stimulating in an academic sense. They speak to questions that matter, questions about how common the conditions for life are in the galaxy, about whether water and energy and chemistry conspire to produce biology not only on Earth and perhaps on Mars, but in frozen worlds at the edge of solar systems, bathed in the weak light of stars across distances we can barely conceive. If 4 or 5 of the moons of Uranus are ocean worlds, we are not talking about 1 or 2 special places in the outer solar system. We are talking about a pattern, a suggestion that ocean worlds may be a normal feature of ice giant systems, rather than rare exceptions. Ice giant systems, in turn, are the dominant planetary architecture around other stars. The implication is not subtle liquid water, and the conditions that accompany it may be vastly more common in the universe than our Earth-centered intuition suggests. Jim Elliot spent a career pointing telescopes at moments of darkness, watching stars disappear behind planets and moons, learning the geometry of hidden worlds from the shadow they cast on the light behind them. He discovered Uranus's rings by watching a star blink out in patterns he had not expected. He discovered Pluto's atmosphere by watching a star disappear too slowly. The technique is a perfect metaphor. We learn the shape of what we cannot see from the way it modifies what we can. Science is often like this. The unknown leaves its fingerprint on the known, and a careful observer reads the print and reconstructs the hand. The moons of Uranus have not erupted plumes for us to fly through. The icy mantle has not cracked and shown us its interior. The magnetic field has not disclosed the mechanism of its generation. But it has left fingerprints everywhere. In the anomalous weakness of the radiation belts, in the tilted and offset polarity that makes no sense for a core-generated dynamo, in the cycling magnetosphere that opens and closes like a valve, in the seasonal energy fluctuations that a single flyby could not capture, in the geological chaos of Miranda's surface, that suggests a history of tidal violence no one has been able to reconstruct. The planet has been communicating in the language of fingerprints for 40 years. We have been reading those fingerprints from 2.87 billion kilometers away, with telescopes designed for other purposes, and we have found enough to know that we are missing most of what there is to find. Somewhere in the trajectory of the Uranus orbiter and probe, if it launches in 2031, if it arrives in T43, a scientist who is currently in a classroom, or perhaps not yet born, will receive the first high-resolution gravity field maps of Uranus's interior, and see for the first time whether there is a distinct rocky core or a gradual compositional gradient. Will receive the atmospheric probe data and read, for the first time, the noble gas abundances that encode the planet's birthplace. Will make the first sustained measurements of the tumbling, switching magnetosphere, and begin to understand the mechanism that generates it. Will photograph the surface of Ariel or Titania in the kind of detail that allows geological history to be read, and may find evidence of an ocean that has been sitting there, silently, for billions of years. That scientist does not know yet what they are going to find. They may not know yet that they are going to be the one who finds it. They may be studying biology rather than astronomy at this moment, without any idea that in 30 years they will be processing the first detailed images of the floor of an ice-covered ocean on a moon orbiting a planet that rolls sideways through the outer solar system. Science doesn't give us endings, it gives us a succession of horizons, each one revealing the outline of the next. We thought Uranus was a cold, dead, simple world. It turned out to be a thermally complex, dynamically active, magnetically extraordinary planet surrounded by potential ocean worlds, ringed in dark structures of uncertain origin, tumbling through space with a geological story locked inside it that we have barely begun to read. Every answer we have found has disclosed a deeper question. Every instrument we have trained on that pale blue-green disk has returned data that simultaneously resolved something and opened something else. What is Uranus really made of, all the way down to its centre? Why is its magnetic field broken in exactly the way that it is? Did the moons of Uranus form in the aftermath of the same giant impact that tipped it sideways? And if so, what does that tell us about the habitability of worlds born from catastrophe? These questions don't need an answer right now. They need to stay alive, vivid and unresolved. Long enough for the right instruments to arrive, the planet will wait. It has been waiting, rolling steadily through its sideways orbit, for 4.5 billion years. 21 years of light, 21 years of dark. We are, in the broad sweep of cosmic time, barely in the conversation, but we have noticed. And noticing truly, carefully, curiously noticing is always where it begins.